So our next speaker is Clemens. He's been working for global phasing for quite a long time. He's been very helpful for a while with CCP4BB, and he's going to tell us why he's on a quest for unmerged data.
Good morning, everybody, and thank you to the organizers for the opportunity to hopefully present both subtle details as well as maybe some interesting insights into X-ray diffraction data. We are not directly investigating the space between black spots here, but will definitely look beyond the standard mean intensity of an MX experiment. First, give some background information so that everyone knows where we're coming from in this talk. This should all be familiar to you, since it will involve models, data deposition, and data quality metrics, but maybe with some interesting and useful emphasis. We will look at unmerged data in much more detail to show the real added value this can provide to everyone when made available for each deposited model. Obviously, unmerged data is only ever a summary of the raw diffraction data itself, so we'll venture a bit into this area as well. Over the last few years, we've been heavily involved in the PDB-X-MMSIF working group, especially the data processing subgroup, where we are working with a small but very knowledgeable and dedicated group of people to improve and extend the dictionary. Ultimately, we want to provide ways for richer reflection data depositions that would sit somewhere halfway between the merged mean intensities or amplitudes that we usually see and the raw diffraction images themselves. But we need to show that there is real added value to depositors and users of repositories for doing this. Otherwise, these extensions will not be adopted and opportunities will be lost. So how are we doing in general when it comes to changing our ways and embracing new opportunities? Well, when it comes to data quality metrics and general descriptors for our reflection data, we are often way behind new developments, sometimes embarrassingly so. It took more than 10 years from the first papers to the first PDB depositions, actually providing more useful data quality indicators than the traditional R-merge. Recently, we've been doing a bit better, for example, with the introduction and use of CC1/2. Hopefully, the turnaround time between the introduction of a descriptor, its inclusion into the dictionary, and the subsequent use and user depositions will become shorter and therefore more productive. The work of the PDB-X-MMSIF subgroup definitely points towards that brighter future, I think. But even if we have those metrics reported with a PDB entry, how reliable are those values if there's no way of validating them at all? What are we to make of PDB entries that have overall CC1/2 values below 40%, or of those with a reported overall mean I over sig I value above 1,000? Are these just typos, deposition errors, harvesting software bugs, or real data descriptions? If the unmerged data was an intrinsic part of deposition, we would at least have the opportunity of validating the reported metrics against the actual data. Unfortunately, unmerged data is only available for a very small fraction of the whole PDB, 0.5% of all entries with deposited experimental data. And a lot of those are not even providing the kind of information we would like to see, and which would make them actually useful in the first place. Hopefully, the recent addition to the dictionaries and developments in widely used software packages should make it easier to not only capture that information, but also help users with the actual deposition process. Of course, there's still work to be done, especially at that user to PDB deposition interface. But in the next part, we hope to be able to show you some real benefits of that work. Here's an example where the stored data quality metrics are clearly only a seemingly random subset of those provided in the original publication. Something must have gone wrong in filling out the deposition form, or when some software component was automatically extracting values from a log file. But the 5URO paper shows that the data does not have an overall I over sig I value of only 1.34, and a CC1/2 value was available after all. So missing or incorrect data quality metric values can often be recovered or corrected by going back to the original publication, but who is going to do all that? Checking thousands of partially incomplete or suspicious PDB entries. And what if no publication is available at the time of deposition, or never at all? Originally, nearly every PDB entry was accompanied by at least one primary publication with the full details of data processing and data quality metrics. But there has been a steady increase in depositions that do not have a paper associated with them at all, ever. And that trend seems to be increasing, so that about a quarter of all new PDB entries fall into that category. If we don't have a paper to check for data quality, what can we do? Luckily, 5URO has also unmerged data deposited, although without any additional information like image number or detector position, but it is enough to compute a full set of data quality metrics that show us that this is a rather nice, high-quality data set. Is there anything else we can do apart from validating data quality metrics or computing a full set of them? If the unmerged reflection data, for example, contains information about image numbers, we can compute various quantities as a function of image number. And in the case of 7xVy, for example, this shows us that the data at the beginning and at the end of the 360-degree scan seems significantly worse than the rest, at least judging from the R factors and the fitness parameter as a function of image number. So we could use that deposited unmerged data and just remerge the data after exclusion of those outer regions. This gives us a second set of data quality metrics, with obviously lower multiplicity since we are rejecting 25% of the original images, but otherwise some improved indicators like overall I over SIG-I or outer shell CC1/2. It also seems to translate into slightly better final R and R3 values if refining against this new subset of remerged reflection data, even if that will probably not make a big difference in the final interpretation of the overall structure here. Another opportunity unmerged reflection data provides is analysis for data anisotropy, especially if a full set of uncut integrated intensities is provided. This is the case for both 8AB3 and 6RAB, two examples shown here. 8AB3 was refined against 2.6 angstrom data, while the star and ISO analysis of the deposited 1.45 angstrom unmerged data shows diffraction in the best direction up to 1.9 angstrom. So potentially significant data was excluded from refinement in this case. 6RAB, on the other hand, was refined against 2 angstrom data, while the star and ISO analysis of the deposited 1.28 angstrom unmerged data shows strong anisotropy, with the weakest direction going only to about 2.9 angstrom. In this case, some noisy and insignificant data would have been included into the refinement and density map calculation. But apart from the separate question of anisotropy, its proper analysis, treatment, what effect it could have on the resulting density maps, this kind of analysis makes it clearer what the single resolution value attached to those PDB entries actually might mean. Clearly, 8AB3 is probably a bit better than the 2.6 angstrom value suggests, while 6RAB is possibly a bit lower than the 1.96 angstrom value attached to it. Let's move to another topic we have been investigating now for quite a few years, reflection auditing. We want to understand why particular reflections or group of reflections have a low likelihood value for the final refined model. So at the end of a Buster refinement, the log likelihood value of each reflection is plotted in various ways, for example, as a function of resolution. So reflections with lowest log likelihood values are of particular interest here. We usually concentrate on those below 7 sigma, representing extreme outliers. These plots include markers for known ice ring resolutions, which can highlight obvious problems with ice contamination. Instead of looking at a whole class of reflections, like those within known ice ring resolution ranges, it can also be interesting to look at single reflections, for example, very low resolution outliers. Those low resolution outliers are often due to inadequate beam stop masking, as in the case of the 110 reflection in 5OFB. The actual beam stop shadow, shown on the bottom right, has some artifacts that cause problems in the automatic beam stop masking done by the DevPick step in XDS. The top right picture shows the resulting beam stop mask, while the bottom right shows a single measurement of the 110 reflection, as it is clearly impacted by the beam stop shadow and should therefore be rejected as an outlier already during integration. Here's a case where we have a surprisingly large number of seemingly poor reflections, not in a certain resolution shell, but rather scattered over the medium resolution range. 6VZU is a 2 angstrom deposited structure where the deposited images could also be reprocessed to about 1.7 angstrom resolution, so a little bit higher than the original data, but that is not of real interest for the investigation here. When looking at all the measurements of those outlier reflections shown on the previous slide and plotting the number of outlier measurements as a function of image number, we see some very distinct features. 2 regions 180 degrees apart from each other that have a much higher number of measurements contributing to those outliers than the rest. And if you look at those measurements now not as a function of image number, but by their location on the detector surface, we can see that these are not randomly scattered, but clustered towards a region furthest away from the rotation axis. Since we know the unit cell dimension, Z-axis is the longest with 170 angstroms. We have a nearly orthorhombic unit cell, and the crystal orientation, B star nearly parallel to the spindle axis. We can make an educated guess for the reason those reflections behave as outliers during refinement. At the two segments 180 degrees apart from each other, we have spatial overlap of reflections due to the white slicing employed in data collection. The last example to show the added value of unmerged data being available as a point of modeling and refinement has to do with radiation damage and its visualization. You have heard already yesterday by Catherine Shelley about radiation damage, and the work by Kaya Dideres regarding zero-dose interpolation comes to mind as well. Here we want to show you some simple tools for visualizing potential radiation damage at the map level and how it could help finding the best model parameterization during refinement. The first step involves analysis of cumulative completeness as a function of image number in order to define two additional sets of merged intensities or amplitudes. So early and late data sets that contain the minimum number of images from either end, where we still obtain a fairly complete set of data. Please note that this does not involve any additional or new scaling of those subsets of images, only two separate merging steps. We can look again at 6VZU, where we can split the dataset just about into two. This is not ideal for the kind of radiation damage analysis that we want to do here, since the potential dose difference between the two datasets will be rather small. However, the compounds bound to the protein here have an interesting feature: carboxyl groups similar to aspartate and glutamate residues in the protein, and these are known to suffer from radiation damage. So the electron density map of this binding site in 6VCU is very nice and clear, but the so-called F early minus F late maps show some very large features at several functional groups. This kind of difference map will be positive where electrons are present in the early data but have disappeared in the late one. And it is negative where new electrons have appeared in the late dataset, but this is often a much less pronounced feature. We can clearly see radiation damage of several carboxyl groups, asp glue residues lighting the binding site, and two of the carboxyl groups of the ligand itself. There's also some interesting difference density on the arginine side chain. This is most likely due to an increase in temperature factor when the surrounding asp glue side chains get damaged. The third carboxyl group of the bound compound seems to be less susceptible to radiation damage than the other two. If we look at the whole structure with the F early minus F late map shown, we can nicely see hotspots and connected regions in all four molecules of the atomic unit. Another example is 5KCO, where the bound compound contains now a chloride atom. The electron density and difference density maps in the lower left picture are very clean, so parameterization of the model as deposited seems to be adequate to describe the model and match with the overall data. But the F early minus F late map shows a clear peak at the chlorine position, suggesting radiation damage. Should that have an impact on the parameterization we should use here? Well, we have mainly two parameters to play with when it comes to describing the situation: the occupancy and temperature factor of an atom or a group of atoms. Looking at the deposited model, we can see that the common occupancy of 0.84 for all atoms within the compound was used originally, and that gave an average B factor for the non-chlorine atoms in the compound of 18 angstroms squared, while the chloride itself has a much higher value of 32. After re-refinement using Buster results in a similar picture. Independent of the type of data that we use, original, re-merged, or reprocessed, it doesn't matter. The temperature factor for the chlorine atom just sticks out. What we can do, however, is to split the occupancy of the compound atoms into one for the chlorine alone and a grouped occupancy for all others. In that case, the temperature factors will become much more similar, 19 and 20, while it's the occupancies that start to differ, 0.79 versus 0.39. We can even do a limited refinement, B in occupancy only, against the two subsets of data. The two last rows show that it is the occupancy of the chlorine atom that shows the most significant difference, 0.46 for the early and 0.27 for the late data. So it seems that the parameterization with a split occupancy but similar B factors is probably a more accurate representation of the mean data used in refinement than a single occupancy and widely varying B factors. But without the availability of the F early minus F late data sets and the resulting difference density map, this distinction would probably be much more complicated to make. As a short summary, we can probably say that merged reflection data as currently required for deposition to the PDB only really contains the absolute minimum of information used for model refinement. while unmerged reflection data, if deposited correctly, already allows for a large number of validation and additional analysis steps that can give more confidence into the quality of the model, but maybe also provide pointers for model improvements. Of course, raw diffraction data is a record of actual experiments, but require a whole other level of infrastructure and metadata. Ultimately, we hope for a similar virtuous cycle as seen when merged reflection data was made compulsory for deposition to the PDB. So we hope much more users take the opportunity and deposit more than just the final set of reflection data coming out of a refinement program. A multi-data block reflection MMSIF file with various sets of merged as well as unmerged data should not be a scary proposition and would provide real added value to both users and software developers. So I would like to thank all my colleagues at Global Phasing, the members of the PDBX MMSIF data processing subgroup, and all members of the Global Phasing Consortium. And last but not least, everyone that deposits unmerged reflection data or even raw images. This is very much appreciated. Thank you.